Alright, hello and welcome to another physics problem tutorial. There's a lawnmower outside, that's going to be annoying. Alright, so today we are working through problem number 39 in chapter 12, which talks about static equilibrium. So let's read through our question. We have a guy on a ladder. There is a cord in between it that has a tension, let's say T. This guy has walked a distance D, let's call it. I know we have a number for it, but we're going to use D for now. So let's say he walks a distance D up this ladder of length L. And there is a tension T. There's also hinge forces up here. And there are normal forces from the ground that point upwards that support the ladder. And we want the tension and the normal forces. So, as always with static equilibriums, let's draw free body diagrams. Although in this question, let's draw free body diagrams for the two sides of the ladder because they give us the hint too. So let's draw them down here to save space. So we have the left side, which has a hinge force in the x direction, a hinge force to the y direction, and it has the guy's weight on it, mg, a tension force T, and a normal force N1. For the right side of the ladder is a lot less complicated. You have, by Newton's third law, an equal and opposite hinge force, another equal and opposite hinge force, like that. Again, a T to the left this time, and an N2 here. It's not totally to scale, but that's not important. So, and again with static equilibrium questions, what we want to do is write out torque, Fx and Fy equations. So, let's start with the torque equation about the hinge because we don't want to be messing around with these hinge forces. So, on the left side, by the way, we can find the angle because we know this length and we know this length. So we can do an inverse sine. And if you do that, you should get that this angle is 18.2 degrees. Don't round to 18. Your answers will be a little bit off. So we get that this angle is 18.2 degrees. So we can see that the torque from mg will be, so if we write torque net, will be mg times the distance away from the rotating point, which is L minus d, times the sine of the angle, which will here be sine 18. Similarly, the tension also exerts a torque in the same direction. So its torque will be T times L over 2 times sine 72. Or I guess this one will be 18.2 and this one is 71.8. So we have these two torques, and in the opposite direction to balance them, we have a torque from N1, which will be a minus N1 times L times sine 18.2. Now, next we can do a torque equation for the right side of the ladder. So in this direction, we have torque net again. So we have T times L over 2 times sine 71.8. And then to balance that, we have N2. So we have N2 L sine 18.2. So, but if you notice, we have three variables, T, N1, and N2, and only two equations. So to get our third equation, let's think of the ladder as a whole. So there's no net hinge force, there's no net tension force. The only net forces on this ladder as a whole will be mg and the two normal forces. So we can write that mg equals N1 plus N2. And as always with static equilibrium, the net torque equation is equal 0. So you can see that we now have three equations for three variables. So let's solve. So I think what I want to do is find N1 and N2 in terms of T to plug them into this third equation so that we can find T and then find N1 and N2 off of those. So let's do that. So if we start with the first equation, if we add N1 L sine 18.2 over and then divide by L sine 18.2, we can see that we have N1 isolated. And then that equation will look something like this. So if I write all this equation out, now we have a formula for N1. So all of that. These equations will get pretty big, unfortunately. So similarly, for N2, we'll add this term over and divide by L sine 18.2 to get that N2 equals T L over 2 sine 71.8 over L sine 18.2. I could cancel the L, but I'm not going to. You'll see why. So now we can plug in these values of N1 and N2 into this equation. So we get that mg equals mg L minus d sine 18.2 plus TL over 2 sine 71.8 over L sine 18.2. And then we also have plus TL over 2 sine 71.8. I'm missing these decimal points. L sine 18.2. So if you notice now that we have a common denominator, which is why I left this L. So we can simplify this into mg L minus d sine 18.2. And if you notice, these two terms both have this L over 2, so we can turn these into an L. So we have plus TL sine 71.8 over L sine 18.2. So now we have one equation for one variable, which is t. So let's solve for t. So if we multiply L sine 18.2 and then subtract mgl minus d sine 18.2, and then we divide L sine 71.8, I'm not writing out these steps, but because my room is limited. But if I do all of that, we'll end up with something like mg L sine 18.2 minus mg L minus d sine 18.2 all over L sine 71.8. All of this will equal t. And if you plug in all these known values into these calculator, you'll find that your tension force should be 207 newtons. Alright, so that's our part A for the tension. The last two parts, which are N1 and N2, are much easier because now we can just plug our value of t into these equations, which should give you that N1, if you've done your steps correctly and plugged it in right, you should get N1 equals 539 newtons, and that N2 equals 315 newtons. Alright, I hope this tutorial has helped you with static equilibrium. Remember that you always want to write out your equations for torque, Fx, and Fy, and also remember to never mess with hinge forces. Alright, thank you for watching. Bye.